So what I'm starting with here is pretty much just, well, almost exactly the base project that I put on the same page as the first 3D lab. So I think it's called Lab 3. It's called the first 3D lab, where we kind of set up three-dimensional objects, set up some viewing, and get things to move around a little. The only thing I've added here to that before I started this lecture is I've actually implemented a camera class. But implementing this camera class is kind of what you do in the Lab 3. So the Lab 3 is a step-by-step implementing the camera class, getting this viewing to work, getting transformations to work in 3 dimensions. You get there, both the matrix class and the model matrix class, not completely fully implemented. You need to implement some of the rotations as well in the model matrix, but this is more or less what you get, except for the camera class that I've added here. But to begin with, the game class here is exactly the same as you get there. So if you import that, I actually put a new version using Java 10 and using the latest Eclipse. So I hope there will be a version that everyone can import without getting errors on it, but we'll see. Still, we have the problem of when you import it the first time, you have to go and go into run configurations and arguments and select other, not have the default, select other workspace and select the assets folder as the base folder for where the program is running from. Other than that, everything should be pretty much importable and exactly the way it is like this. And when you run this, what happens is basically this. We have a 3-dimensional cube there, and we're looking at it. So what I want to do now is look a little bit at the code that's behind this. Like, how does this work? Look at where we're building this view matrix mainly. I'm not going to go into the projection matrix specifically. We're going to look at that later on. But look at the view matrix, which is the matrix that kind of wraps the position and orientation of the camera, the point of view of the scene, and of course the model matrix, which wraps the position and orientation of the object that we're drawing. So before we start, are there any questions on this or on the assignment that you're doing now? Something that we can start off with? Everything going well with that assignment? Yes? Okay. Nice. All right, so we've looked at the model matrix before, and kind of the main thing here in the matrix class here is this set shader matrix here, where we actually send it into the shader, and we can look at the new shader as well. So if we go here into the vertex shader, it's now called Simple 3D. You can see that, as before, this is just a fairly simple C program. Now I can make this bigger. No, this is still not. So it's a fairly simple C program here. The difference here is, whereas before we only had position, now we also have normal. So we'll look better at that when we go into the lighting calculations. We have the model matrix, but we also have the view matrix and the projection matrix. And if we go through what's happening here in regards to what the vertex shader does, is it kind of builds the position. Since the position is only 3, it kind of adds a 1 at the end. Then it takes the model matrix and multiplies it with that position. So it gets a new position. This would now be the global coordinates. It does the same with the normal, actually, and it takes the normal out of the kind of local coordinates and into the global coordinates. Now that we have those, see the normal there. Okay, yeah, we're doing the lighting calculations in I coordinates. So the next thing we do is we take the position, we multiply it with a view matrix. In this case, we also take the normal and multiply it with a view matrix. However, in some cases, we will instead do lighting calculations in global coordinates, and then it's not necessary to take the normal any further. So we go by multiplying with a model matrix from local to global. By multiplying with a view matrix, we're going from global to I coordinates, or the coordinates as relative to the camera. And now we're kind of in the camera's own coordinate system. We do very simple lighting calculations, and I'm not going to explain them anymore right now. This is just super simple. Gives us a simple color. And finally, we take the projection matrix and we multiply that with the position as well, and put this into this fixed variable in OpenGL called GL position. So this is not one of the variables we make, it's one of OpenGL's own variables. And it's the only variable that we are required to set to something in the vertex shader, because OpenGL expects us to set that variable so that it can continue on with that particular variable, GL position, onto the rest of the OpenGL pipeline. Okay, so this is what the shader does. And the only things we need to understand really is it just takes our position and multiplies it with the model matrix to go to global, with the view matrix to go to the I coordinates, the camera's coordinates, and then lighting and projection is something we'll look at next week, or projection first, then lighting. Any questions regarding the shader itself? I've drawn this in images, and then I basically draw a big box and say this is the model matrix, and we go through that transformation, and then I draw another box and say this is the view matrix, we go through that transformation. In code, it's just like this. Model matrix multiplied by our coordinates makes a new set of coordinates, just a new representation of the coordinates. Okay, so that's happening in the shader, and we kind of need to understand a little bit, once we add the camera class, about how we're taking this matrix and putting it into this view matrix variable in the shader itself. Okay, so let's look at, to start somewhere, let's look at our display function. We can see the update function is doing more or less nothing. We're not moving anything, there's nothing happening really. We're clearing the color buffer bit as we have been doing before. What we add now is we're clearing the depth buffer bit as well. Because when we're in 3 dimensions, things are actually closer or further away. OpenGL needs a way to know if something should obscure something else. We may not necessarily draw what's behind first and what's in front second. In 2 dimensions, we'll do that. If we want something in front, we just draw it later. That's no problem. In 3D, we have to make sure that the things that are supposed to be closer actually obscure the things that are supposed to be further away if they end up in the same pixel. So in order to do that, we have a depth buffer. This is something we're going to learn a lot more about later on in the course. But just remember that it's not enough to clear the color buffer bit. We need to clear the depth buffer as well, so that every frame we start with a fresh depth buffer and a fresh color buffer and start drawing into those. Here we're simply setting a color. This is kind of back to a very raw way of doing that, whereas I had this kind of set color function last time around. Either way, you can put this in a separate function. You can put this, you can even make a specific class, like we have point 3D and vector 3D. You can make a color 3 or color 4 class to kind of keep track of colors. Then we just start working with a model matrix. Load an identity at the beginning of each frame to start fresh. Nice to have push matrix and pop matrix before we do anything, but in this case, actually push matrix and pop matrix doesn't really affect the scene since we're only drawing one thing. Here's a scale. That's just a scale to 1, so nothing special is happening. Set the shader matrix, and then we go to box graphic, draw solid cube. Should we look at that class a little bit? I do it in a video as well that comes along with the first 3D lab. So we can see there's a lot more vertices in the vertex array. Mainly because, well, one thing is there's 3 dimensions, so every vertex has 3 numbers now rather than 2. The other thing is the cube has 8 corners rather than the 4 we had before. And also, just depending on the order in which we draw this, we may have to repeat some of the corners because we're not kind of indexing into this vertex buffer. Instead, we're just saying the vertex area is the order in which we draw. And in some cases, we'll have to go through the same vertices again, drawing different polygons or different triangles using the same vertices. So it's a lot of points here. This is covered better in the lab and in the accompanying video there. So again, we have a normal area as well. So when we actually go here, instead of there just being one vertex attribute pointer, there's one for the vertex and another one for the normal. And then here you can see we draw each side. So the first side is drawn here. It's 4 vertices. The next one, another 4 vertices, so on and so forth. We draw each side as a single entity. You can set this up so that it kind of draws 4 of the sides in a row, kind of around the cube, and then does the ends separately. Then you might have a bit fewer vertices. In this case, this is kind of clearer. So solid cube, I have something called an outline cube as well. The only difference is triangle fan here, whereas line loop is used here. Any other important things here? Not really, nothing that isn't kind of covered in the lab and understand as we go along. So back to the game, we can actually look at what this looks like if we change it from draw solid cube to draw outline cube, was it? So then we have a cube that looks like that. Yeah, it seems that it's missing sides. We'll see when we start moving it around if we can make it. It'll look better that way. It's disappearing into something at this point. Okay, so if we just start with the idea of using transformations and just getting a sense of how they work in 3D. We have scale here. We can, as before, let's just try scaling one of the sides more than the others and scale the y coordinates more. Okay, now we've stretched it a little bit up. We can make the other ones smaller or different in some way. So now I've got a way to take this cube and kind of make a wall out of it or make something else out of it. So the cube is still just the same, box graphic is just the same set of coordinates going from -0.5 to 0.5 in all dimensions. So it's just one each side, which is the base model that we're drawing. But by using scale alone, we can make a lot of different things out of it. We can make different cubes here. Again, when we set up here, box graphic, we simply create it. And so now we've created the vertex buffer, and we use the same vertex buffer every time we draw a cube. So if we want to draw more than one, we can simply take here, let's just take this set of code here. Let's say for each one we want to make, let's simplify it a little bit. For each one we start with a push, we end with a pop, and we know that the matrix is going to be the same after we draw it. So in this case, we might want to go and say, start with a translation. Add translation. So we'll move this one to the side. We can also get a feel for the kind of size of or the dimensions of the environment that we're working with here, just by kind of moving things around. Let's say just move it 2 to the side, draw another one, and kind of see what that means, where that ends up. Okay, so it ends up fairly far to the side. So X is angled a little bit. So that's another thing that we can look at with the camera. We're kind of looking at it from a little bit of a diagonal. So if we go here and just look at how we're calling this function here, look 3D, not what's inside it, but just how we're calling it. You can read through what's inside it as well when you start the lab assignment, and then you can move it into the camera class. But what we're doing to call it is we're just saying, where do we want to be? What are we looking at? So in this case, let's maybe line it up a little bit and say, let's not be anywhere to the side. Let's just have the camera straight in X, have it it's straight in Y as well, and we're just looking directly like we're looking at it when I draw it on the whiteboard, and just be a little bit away in the Z dimension. Now we're going to be 0, 0 in the XY plane, and then just a little bit back, and then we're drawing things in the center. So the camera is a little bit back, but it's looking at the center, and the up vector is just 0, 1, 0 in this case. Okay, so now we just see kind of exactly the side of that, like one side of that. You can see the other one was moved off to the side. It's a very narrow camera, it would seem. So let's move it just a little bit less. Let's move it one to the side. Okay, so now they're side by side. However, by looking at it so straight, we're not really getting the 3D image. So that's the reason it started out kind of on an offset with the camera. So we have a rotation, we have a translation here. Let's make the second box just without any scale. One on each side. All right. And then we can add a little bit of a rotation. Only have a Z rotation here. So if we're going to add different rotations, we're going to have to implement those. So we need some angle. Let's just say 30 degrees. Okay, so we get a little bit of a rotation there. However, since we want to actually see this in 3 dimensions, it's nice to actually take the camera and where do we have that? Here. And move it. We can start by moving it just a little bit up and a very small amount to the side. Oh no. Like that. It makes a difference. Okay, and now I can see kind of on top of that same scene, except we've moved the camera to a different spot. Now I can do more or less the same as we did before. We can come in and we can say, let's make a float, something like rotation angle. And then go into update and say, make this kind of go one circle in every 2 seconds, 180 degrees per second.
You have to call update somewhere.
I am calling update and display and render. So
updating.
So update is just part of the loop. Actually, I've added one more part of the loop here. So if you look at the render function is just called endlessly. It's just the loop that libGDX calls constantly. First one is input to check if buttons are pressed or if I want to make changes like that. Update, which makes all the updates to my model. And then finally it calls display. So every single frame, input, update, and display will be called.
Yeah, but you're not doing anything with rotation angle, are you?
No, I'm not using it yet.
Okay.
So I was going to go here and instead of 30 degrees, put in rotation angle, like so. Kind of see how that works. All right, so in this case, we have a little motion there. We've added a variable that's constantly changing, and we've added that to the rotation. So if we want to, well, we can do more things here, like make one thing rotate around another, and say, let's take something like, wait. If we take rotation angle here, and skip the translation here first, or copy it to here. Then we can go, let's say 3 to the side, or will that be too big? So we won't see it. To the side, so we've rotated, then we translate along this rotated coordinate frame. So at that point, we're somewhere.
We're currently rotating around the origin.
Yeah, so now we're rotating around the origin. Next, we might want to say, all right, since this one is going to be traveling big here, let's make it small itself. See what happens here. Okay, so that one's going around the origin. What do I need to do in order for it not to kind of turn the same side to the origin all the time, but kind of get it to actually keep still or keep its own orientation? Can I do that?
Add a translation.
Well, I've added a rotation around the center, and then I've added a translation there, but it's translating in a rotated coordinate frame. I'd like to do something like take the original rotation out then, but I can't really use a push pop for that because I need the translation, and the translation happens within the rotated one. So what can I do in order for it to move around kind of like this, rather than this? Yeah, just add another rotation and make that rotation after I translate. What should this rotation be to cancel the other one out?
The opposite of it?
Yeah. So if I rotate and I translate, then I kind of rotate back to get back to my original rotation. This is just something that's kind of fun to play around with. So now the cube is kind of keeping its own orientation in there. Looks kind of unsmooth here on the projector. Sorry?
Looks like it only has 2 sides.
Yeah, because there's a lot of shade. So the lighting in this case is just kind of a single light coming straight from the camera. So the camera kind of needs to face a particular polygon or a particular face of the object in order for it to light up properly. All right. What could I do now? And now I'm just thinking about kind of using these functions, not the underlying math. Like I have a function that we looked at earlier, like how we use it, which was setting up the camera. How can I now make the camera look at that rotating cube the whole time, instead of looking at the center, following that rotating cube around? So I want the camera to be still, but like I'm a cameraman and I'm just following that around with my point of view. I'm just trying to look constantly at that point. Where would we change our code for that? To begin with, where are we now setting up our camera? Okay, in create.
We want to do it in update.
We might want to do it, yeah, in update. Update would be a nice place if we're not actually putting stuff into display. So update would be the place, yes. So if you take a look here, it's okay to start with some look here just to have a base there. But if we go into update, so look is a function that, if we kind of look at the matrix here, it's a little bit complicated here because we're not using the camera class, because look is doing both. It's both setting something to actual OpenGL and it's changing things. In general, using the camera class, we'd like to do rotations and looks and stuff like that in update. And then in display, we'd like to say, we're just going to take our matrix and put it into OpenGL. This particular function is doing both. So using this version of the function could be done both in update or display. It doesn't really matter. But very soon now, in a few minutes, we'll try to move it into the camera class, and then we'll split this up and have the actual changing of values happen in update, but the putting those values into OpenGL happen in display. The main thing is we need to do it somewhere that happens in the render loop. It's not enough to do it in create, because now we want to make a new look every single frame. We want every single frame to have a new point of view, so we have to change the camera every time. So what would we put in here now? we need the center point of cube. So that's kind of tricky, isn't it? Because now the cube is, we're kind of making it on the fly. We don't have a class that's a particular cube and it's moving and it can give us its location. So we kind of have to calculate that. But how could we calculate that? Like, let's just do the same things that we're doing here. We can even just make a new model matrix. It'd be a long way around, but let's do it for the sake of just doing this
You do the
cleanly
sine
here.
and cosine of position factor.
So we don't actually have to do the calculations. Can anyone see what I'm kind of doing now? I'm going to use my model matrix. It can do these things. For instance, if I add this rotation, add this translation, add this rotation, even add this scale, I have made the same coordinate frame as the one that I'm using here when I draw this. Except now I'm just going to do it in this local coordinate frame. I could use main as well. I'm not using main for anything else here, but I'm just to make it clear that model matrix is just a class. We can make an instance of that class and we can use it. What can I now get out of model matrix? Like this model matrix MM now has values. I've added these transformations. Can I now access its values?
You can get like a get vector, or yeah, get A, B, C, and D.
These are the vectors. I'm really interested in the position. So get origin.
Don't you want that in where you have new point?
Yeah. So I'd actually want to just put that in here. This is maybe not, in the end, we'd have things in classes. We'd like to have that box in a class and it can tell us its location. We'd like to have a camera class rather than doing it like this, and the camera can kind of keep track of this. But sometimes you just need the location of something in the world, and you kind of need to track your way to it or backtrack your way away from it. It's okay to just make a new model matrix, do the same transformations to that, and then use that functionality rather than kind of implement it over and over again. So I'm simply using the functionality of the model matrix by adding a rotation, a translation, another rotation, and a scale. The scale doesn't matter actually in this case because it doesn't affect the point of origin. It would affect it if it would happen earlier, but at this point it doesn't. And then simply get the origin and say this is going to be my center point.
Return 4 points. Or does it only return the first 3? Does the origin return the one at the bottom or no?
From the matrix.
Yeah. I just don't remember. Does it return?
It returns kind of just the point, the position of the model matrix. And then you have A, B, and C, which are the vectors, the orientation. So origin is the position, A, B, and C together are the orientation. So let's see how this works. It doesn't. All right. Why is look3D not being called?
It's a display.
We can move it to display, but is it being overridden somewhere here? It shouldn't be. Let's see. All right. Now what we'd like to do is something like let's do system out print line. It's always a nice way to kind of see if things are actually what you want them to be. Maybe it's not changing at all. change that. But is this? Yeah, I'm missing the plus. These two spots. Two. Okay, so I'm always getting 0 from that.
Did you set the null matrix to the identity matrix?
No, but it should still be giving me some values. Yeah, add translation actually. Changes, blah, blah. Get origin. Right. Am I doing, no? And then new model matrix. We can do that first. Load identity matrix, but it shouldn't, it would give me some values though, and I'm changing those values constantly. All right. Okay. So my mistake here was, as was pointed out, thank you very much, that I didn't load the identity matrix. I actually would have thought that that mistake would mean I just get really, really weird stuff. Then I'd say, okay, I didn't load the identity matrix, so I'm just getting numbers that are out of whack. Instead, I seem to get 0 all the time, which I'm not sure. Yeah, of course, yes, that's correct. The matrix I had was just all zeros, not the diagonal line of 1. Thank you. All right, so now we're actually have the camera following that around, which looks more like the big box is going around the small box in this case, but that's another kind of reminder that everything in computer graphics and 3D graphics is going to be relative. You know, what we're going to see is the relative position of the objects to the camera location that we picked. If we move all of these by the same amount, we're going to get the same image, even if all of them have different locations. If we scale everything up by the same amount, we're going to get the exactly the same image, even though in one case, you know, everything is sized 0.01 units, and in another case, it's sized 1 million units. We just get the same image if everything is the relatively the same sizes. And in this case, without any background for reference, then obviously it's hard to see which one is moving around which one. You know, is it the camera that's moving? Is it boxes that are moving? What's happening? But what we know though is that the camera is still, the big box is still. However, the camera's point of view is fixed to the small box, and the small box is moving. So this was actually a good error, because it has a little learning opportunity in there. When we just have a matrix full of zeros, all we're going to get is zeros. It doesn't matter how many translations or scales or rotations we add. Everything's just going to end up multiplied with 0. Bunch of zeros. All right, in that case, we can actually probably take this and put it into the update, and it doesn't matter in which side it is. It kind of has stuff that should be in both. So in order to do that, let's look a little bit at the look at function, since that's what we've been kind of looking at this week. So we have this function called look3D. So the first lines, what do those do? Just setting up the camera. And we can just read those. Those are very human readable. They just do exactly what we wrote up on the whiteboard earlier this week. They make n from subtracting center from I. They make u by taking the cross product of the up vector and n. They normalize n and u, and then they make v by taking the cross product of n and u. Here you have access to a nice vector class that simply has the cross product implemented, so that's nice. The only thing I've added in here is this set function. It's not in the version that you get. I just added that so that the camera class would work better. Doesn't matter, you'll see it soon enough. And you can add as many functions as you want. If you want a different way, like in this case, I just needed a different way to set values to the point. I didn't want to have to make a new point every time because of garbage collection and stuff. I just wanted to take a point and set new values to it. So I just added this function set xyz. So you can add as many functions as you want to your vector class. Point class is much simpler because we don't really have, we can add a vector to a point, but that's more or less it. Whereas the vector, we can do dot product, we can do cross product, we can do all kinds of things. And so we have them implemented here in the vector. Dot self is a nice one, which basically gives us the length squared. Length gives us dot self, the square root of that. Yeah, normalize, so on and so forth. We can see that normalize actually has a lot of calculations. So if we can kind of save some of those calculations for later, we can often save a lot of time. Actually normalizing something means that we have to do the dot self, we also have to do the square root, and we also have to do 3 divisions. So kind of saving the actual normalization for the opportune moment where we have to do as few as possible can really save us some time. All right, so that's vector and point. So the next thing is, okay, now we've basically made this coordinate frame. And it's all just happening on the fly here. We're just making this new vector n, u, and v. Then we make a vector that we call minus I. We basically make a vector that has the coordinates, the negative coordinates of the I point. So we can do this minus I dot u thing, which was in the view matrix. Then we just set up the view matrix, and it's simply a matrix. The bottom line here is 0, 0, 0, 1. And then we have ux, uy, uz, and minus I dot u. Vx, Vy, Vz, minus I dot V, and Nx, Ny, Nz, minus I dot N. It's just, we're just loading into the matrix the way we said would work. The inverse matrix of a model matrix, kind of, but with the camera's coordinate frame. All right, when we've set up this matrix, so what I'm trying to kind of underline here is, you know, doing it in a program isn't magic, isn't any different from doing it as math. We're just making those vectors, and then we're just making that matrix, and then we're just sending that matrix into OpenGL. We basically make a new float buffer. The float buffer thing is just kind of class formats and representation that libGDX likes to use. So the only reason I'm doing that is just because we're working inside this libGDX environment. The main thing is just we make the matrix, we send it to the shader. This float buffer thing is something that libGDX just uses as the way to send it into the shader. So we put this matrix in, this floating point in here. You could also just make the floating point buffer already with 16 floats and then put it in there. I just like how clean this looks because it just looks like the matrix. It's just lined up like a 4x4 matrix. So then we put the matrix into the floating point buffer and we send it into the view matrix location. And the view matrix location is simply a handle to a variable in our shader. If we look at that shader, we have the view matrix variable. And what we do with the view matrix is we simply multiply it with the position in one point. That's all we do with this. It's not any more or less complicated than that. It's just exactly what we do on paper when we're making these calculations. Questions regarding this idea of the view matrix being built and sent into the shader? All right.
What does rewind do?
That's a good question. The question is, what does a rewind do? It somehow sets a pointer to the beginning of the matrix so that the next time there's a read operation, no, not on the matrix, on the buffer. So next time there's a read operation, it starts from the beginning. I'm not exactly sure why you need the rewind there, but you kind of need it always at the beginning, especially with the vertex buffers. If you don't do the rewind, it's going to end up trying to read from kind of the end of it, but only at the beginning. After that, you can do as many read operations on it as you want, and you don't need the rewind again. And I've just not dived into why this happens. I've just decided I'll put the rewind there. It works. So I'm sorry.
I was just putting it there because every time you do it, you put the rewind there. So I figured there was some reason for it, but.
Again, so I want to kind of emphasize, and often in the course I like to emphasize this. Let's make it the last thing I emphasize before the break. That we're trying to learn graphics in general, and we're trying to learn OpenGL. But the environment we're using is libGDX, and libGDX is kind of this encapsulation of OpenGL and an encapsulation of a lot of other higher level functionality. So the way we talk to OpenGL is through kind of all this gdx.gl stuff, whereas I'd much rather like to just be able to put the names of the OpenGL functions straight. I'd also want to be able to just take arrays and put them straight in there because it's an array that it ends up in the shader. However, this whole buffer thing is just libGDX's way of moving things around inside its system. It's just a Java util thing though, the buffer, but it's what libGDX likes to use. And so we kind of do that. I always feel like it's kind of a little bit convoluting because it's an extra step in between just the array that we're filling and the array in the shader. But there you have it. This is the environment I decided to work in. And so we have to do the put and the rewind and all that, but you know, it's just Java stuff. So the answer is we just do the rewind. It's some Java stuff. I'm sorry. I wish I could have this cleaner and just focus on the OpenGL function, but sometimes you just have to work with your environment. Let's take a little break and then let's start actually putting all this functionality into the camera class, see how we can kind of make the camera live between iterations and work with that a little bit. Go. I like to do this in order for the people watching the video to know when the break ends. Fast forward.
Já, það sem sérði í raun og veru gera það sem sérði í raun og veru gerast í freiminu þá að taka klárað allt þess. Þannig að þú veist, kassar hérna, já, það svo nálægt, hann fer gong, það fyrir svona tíma og hann eiginlega já, en já, því að hann bara fundur í miðinni og þá raunverulega fer hann inn í sig. Hann fer bara, já. Þannig að því að ég rúpaði gegnum kláðast.
Það er bara Nei, þetta var varmæti sér, ég segi.
Ok, cool. En vandamálið þess að við erum að reyna að gera bönns og má laga þannig í GDX svona. En ekki hafa stundur að gera, það kemur stundum fyrir ef ég það sem gerist náttúrulega, já, við erum bara betur það.
Þegar heildarvirknin að virka, það sé að útreikningarnir eru eins og þeir eru að vera. Já, þarna var, Anna, ég veit að þetta er seifa líka, sko. Nei, þarna, það sem gerðist, þetta partur af glitch hotfixin okkar. Það það að þarna fór kúlan í raun og veru inn í pallið og ég accelerataði inn í pallinu manually aukalega. Þá kemur svona smá klipp, annars klippast það inn í pallið. Þetta partur af hotfixin okkar, það ekki fyrir. En varðandi hitt, sko, að ég sé þetta líka, ég veit ekki hvort það alveg þegar við komum bæði halla á hreyfingu eða snúning eins og ég að þá ertu komin með stærsta time sem að gera ráð fyrir hreyfingur á boltanum. En þú ert kannski að nota línur sem staðir svo líka. Og meðan ef þetta er 100% rétt, þá þurfti náttúrulega líka að taka stærsta time inn í formúluna fyrir snúningum þessu því að ef þú hugsar ramman í heild sinni að hugmyndin er svo taka þessu time að það sér ok, þetta er boltinn í fyrir ramman, þetta er boltinn í lókramman, við þarf að gera útreikning sem að tekur þetta allt með inn í miðjum. Ef þetta er línur sem er að snúast oft snýr maðurinn bara fyrst og segir ok, ég er að taka hreyfingur á boltanum með línuna. Maður ekki gleyma að taka sko í byrjun rammans línan hér og boltinn hér, í lókrammans línan hér og boltinn hér. Þannig að hér er rauninni Og ég að segja, þetta flókið. Það mjög cool að þið þetta allir myndina en þið
reyndum það. Já. Ég reyndi að reyna alltaf að stöða því.
En þetta orðin fólknir bækja, sko. Mjög skemmtilegt þetta. En þau má verða þetta virkar ekki að það. En þú veist, ekki áhugjörð því. Þannig að miða við að bara statískt þegar fallið hlust og ekki hreyfa það í bóttanum og hann virkir það rétt. Og mér takist, það líka heilt. Þegar ég hreyfa fallið hingað, þá hérna í byrjun rammans, hérna í lok rammans, boltinn hérna í byrjun rammans, hérna í lok rammans, þú veist. Þú með regnar út. Punkturinn sem hér eins og verður að gera. Þetta boltinn að gera. Þetta hlutir sem geta komið út og ég byrja ekki nýður fyrir svoleiðis glitcha en þeir reyni umhverfis og allt það er solid. Eins og þessi glitcha á það er svona hallar upp. Gerur þið svo yfir út og þá einhvern veginn náður að veiða eftir á inn?
Já, því að þá er það glitcha á það því að þá gerist það hérna kúlu og svo gerist það kúlan með sem sagt svona kúlan hér þá ég með bugcheckerinn sem segir að T-hittið er mínus þessi hérna á, pluss þessi hérna á, eða mínus þessi hérna á, pluss þessi hérna á, þá veit ég að kúlan er inn í kassanum og þá reyni ég að hreinsa hann út með því að nota vektorinn sem að fá síðast í gegnum og hoppa eftir hérna á. Sem því að þá tók ég þennan hérna og bánsaði.
Það er líka bara góð hugmynd. Það er svona ákveðin leið til að segja að klikka einhvers staðar inn í pappinn og þegar hreinsun getur öll.
Já, en þetta er ekki krökk.
Á endanum eins og það. Þá var það í fyrsta lagi er það eitthvað sem ég hefði örgulega tekið eftir nema að þú verður með á það. Ég veit ekki hvort þið farið í að hafna upp og reyna að veiða bóttan í það.
Búin sérstaklega í ríkið.
Númer 2 er að player verður að spila leikinn og svona glitch verður að gera þetta á hana. Og maður hlýtt að missa bóttanum og maður einhvern veginn að redda sér og misti ekki lífið sig.
Já, en það getur líka
en glitchi sem gerst hins eginn að þú ert að ná honum með einhvern glitchar og þetta í gegnum það getur leikum bra. Þannig að glitchin bjargar þig inn í leikinn þegar það hendur en alltaf, gott um að eitthvað ég var ekki þetta er ekki fyrir spurningar
skilja villast. Já. Og auðvitað hvort var eitthvað sem líka kannski statík sem er misklandi. Þetta er frekar ekkert okkar að
byrja því frekar einhvern veginn að koma einhvern veginn í ritminn og fullkomlega laga einhverja glitcha. En þú veist.
Við erum líka með skólasystem sem er flóðsættum.
Ok. Já, smá sem nálgast þennan. Svo er einhverja skora að það er ekki gert einhverja. Já, en við getum útfært eitthvað svo. Þú hefði ekki séð þessi glitchi sem við talum. En sko það er bara munur á því ef það er þannig að segja svo að setja einhverju bakið sem er svona það sem kemur hér og mér finnst það eins og ég lenda hér einhvern veginn ákveður leikurinn að fara hérna í stæðin. Það er ekkert slóð.
Nei, það er ofta svona sem við erum að koma þarna. Það er ofta eitthvað að passa ekki á skólanum.
Það er eins og það er eitthvað sem getur lagað fyrir einhvern veginn að tjekka út að sé kullurinn hérna og sé hér. Ég getur bara tekið það í ábyrgðinu og sagt ok, ef ég er að koma hérna að þú veist, ok, setur þið það kullurinn í gang og segir ok, þannig að er ég að skoppa niður eða eitthvað en ég getur byrjað að ég segja hefði. Ef það er kullur gegn herra með henni, þá gæti ég aldrei verið að skoppa fleiri. Kullurinn er byrjað sem getur stórt en það er þá ætti hann í rauninni, ef hann heldur að hann sé að lenda okkur hlið, þá segir hann það er ekki hægt. Kuppur hérna, þá er alltaf, þið verður alltaf neðri með henni í staðinn. Og ef ég lendi hérna rétt hjá báðum, þá ég er ákveður að hvort þeirra hverju, það skiptir ekki öllu máli. Aðmálið er það sem er astanlegt, er að það er kuppurinn hérna. Kuppurinn kemur hér og stoppa hingað einhvern veginn, báðir hverju og það er okkur gegn. Það er alltaf pínvík. En það ætti ekki að vera flókið að laga það, eða bara reyna að tjekka inn í griddið. Segja, ég er hérna í griddinu, hér búið ykkur hliðina og er hann sett í hann trú. Ef svo þá bara get ég ekki skopað þessa hlið, þá bara þessi hlið eftir. En ef það er enginn gang, þá þarf að tjekka algoritmi sem þú notar til þess að ákvarða það er ekkert spór ekki að þetta. Ég myndi ekki að fara lengri en það. Get ég tjekka það eins í kringum mig, bara ef það er kubbaðar, þá get ég bara útiloka á hvernig það sem ég gerir skopað, það er bara að vera að flokka. En ekki að fara lengri en það. Ég vilja fá eins og kílógramm sem var með mismunandi massa síðan. Eins og þetta var. En ef við værum með það, þá værum við sjúklega búið. Við pratum eins og þetta og skopað svona. Hvarða fyrir þetta. Því hvaða lendir ég á hvernig skopað og svona. Og hann meirist það ekki núna að það hann hendi alltaf nákvæmlega sem við fyrir. Hann fór hún undir skynið það til það í. Ég myndi reyna aðeins að laga það, en það geti komið inn einhverju ská, einhvern tíkli eða eitthvað smá og eitthvað. Var það tímur sem var þessum? Já, nei, ef það skilur það mátt. Eins og ég segi. Bæði, ég veit ekki hvort ég myndi þetta glitsa sem pínu. Þetta myndi væntanlega að laga kjekka og það myndi ég halda. Það er ekki verið flókið. Þá er það að segja að ég er að kíkja á fólk og það ekki að gera ráð fyrir ég er að kíkja á átti að einu síðan ekki að
Já. Ef þú veist í hvað áttan er að fara, þá eru bara tveir möguleikar. Það þarf ekki að tjekka allan hringinn í kring. Þetta er bara einn eða tvo staði í kring. All right, sorry about that. All right, let's continue here a little bit. So we've looked at the look 3D here a little bit, and we've set up a way to actually change the camera over time. But it'd be nicer to actually get the camera into its own class where it can keep track of these vectors. Here we're just making the vector n on the fly, the u, the v, we're just making it on the fly. We're using it to make a vertex, make a matrix, and sending that into OpenGL, and then none of this lives anymore. So what's more interesting is to say, all right, let's make this camera class, and I'll just have I, V, U, and N as persistent entities in this class. So if I make a new instance of a camera, I have these. Another interesting thing with having the camera class is I can actually make 2 or 3 instances of a camera class. If, for instance, I have a split screen, so I have one camera for one viewpoint, another for another, and I'm kind of drawing it into 2 different viewports. Or maybe I have a top-down view that I display just in the upper right corner or something like that. So I have my main view with my main camera. I don't have to constantly be rebuilding these. I just have one instance of the camera class for my main view. I update that as I walk around, and then I have another one for the top-down view, and I update that depending on my main position, so on and so forth. Then I have this Boolean orthographic. Let's not worry about that until we're into projections. So we'll just put this to false all the time. And this has to do with the projection as well. So let's mainly look at the look function here. I, U, V, and N. So when I build a new camera, I just put some basic values to this, but then I have the function look. And the function look just does exactly the same as the other function we were looking at, except rather than making a new vector, I have these persistent vectors, N, U, and V, and I have my own I. So now I have one function that just does this, just builds the coordinate frame. Very clean, nothing else, just build a coordinate frame with 3 vectors and a point. Then I have these different functions here for slide, for roll, yaw, pitch, so on and so forth. Then I have this function here, get view matrix. And then I do this, the vector minus I here. I make a new floating point matrix, I build the matrix, and I return a buffer. Put it into the buffer, rewind the buffer, return the buffer. So the camera can both know its own orientation, its position, and it can also give me a view matrix. So the camera knows how to give me a view matrix. It also knows how to give me a projection matrix, which we'll look at later. So if I go into my game here, instead of having to call this look3D function, which does all of this, instead, I'm going to go up here and I'm going to say, I'm just going to make an instance of the class camera, call it cam. In my create function, go in here and say cam dot well, let's start by cam equals new camera. We could do a look here. Let's do cam.look just to have some baseline here. So we can just use these same values here. So we're just sending them into the camera instead of directly into this function. And I'm going to take this function out. So new camera, look. So we have some baseline values for the camera. Now I'm going to go in here, and instead of doing look3D here, let's just do nothing to begin with. And say, now I've set up the camera. However, every time I display now, I have to make sure that I actually send the camera into there. So I'm going to look at look3D here, and I'm just going to steal this line, the one that actually sends a buffer into the OpenGL shader, into the vertex shader. And at the beginning of my display function, I'm going to go ahead and call that and say I'm going to send my camera in there.
You're going to do matrix.
Except now I want to do cam dot get view matrix, and then my camera simply gives me a view matrix that fits the current location of the camera. And if we run this now, I'd like to imagine we just get our original point of view. Right, so this is our original point of view. We're not changing it at all. But if we want to get the same functionality as we had before, like we're doing here, we can again say cam.look and send these values in. So we're doing the same thing again. We're just building this position here. Actually, the second rotation and the second scale are irrelevant here because we're only looking for the position. Now I'm putting that into cam. So cam look, if we go back into that, it only changes the current camera's coordinate frame. So that's something we want to put in update. That's just updating values that we ourselves have, updating the camera, just like we update the position of an object or the speed of an object, just updating the camera. However, in display, we have kind of the second half of it, which is taking that, making a matrix out of it and putting it into OpenGL. I've split this up into the update part and into the display part. So now again, our camera is following the small box there and looking around at it. So what we're doing now is something that we might do in an animation. We're updating the camera every frame with a new position and a new look at point. What might be more interesting, especially in something like first-person shooter, is to say, I'm just going to start with my camera somewhere. So in create, let's just say we start with it in 0 and Y, and a little bit backwards in Z. We're going to start with it here. We're not going to be doing all of this, all these updates here. So we're just looking directly on the front of our scene. All right. But now we want to be able to incrementally update our camera, not resetting it every time with a new position and look, but instead just incrementally changing it. Like I want to look a little bit to the side. I want to rotate it a little. I want to move a little bit forward. I want to move a little bit backwards, move up and move down. So if we go into camera, we can see the slide function that we that I kind of very hurriedly put on the whiteboard last time. So slide says how much do I want to go along the u vector, which is kind of my internal x direction. It's going to right and left. The v vector is going kind of up and down. The n vector going forward and backward. So I just change the I using the x, y, and z coordinates of the respective vectors. So delta u will be multiplied with the x, y, and z coordinates of the u vector, put into here, so on and so forth. So the idea is if I put some value in here, I should move to the right or a negative value to the left. Where would that go? Update or display? This incremental change of the camera.
Input.
Or input, actually. Update. Yeah, since I'm kind of splitting update into input and update here. Doesn't matter. We can also, I'd actually like to just keep this clean and say, let's put it in update. Keep it in here. Let's just add this here, and input doesn't matter.
I do think the separation of update and input.
Yeah, I like it as well, separating update into input and update, but I just don't want to convolute this message, which is input is just a part of update. Display is always separate. Display is just taking our kind of static model. We've made all the changes. We've changed the speeds, we've changed the accelerations, we've changed the positions. Now we just have a current model, a static model of our environment. Display just takes those values and displays them, just draws them. All right. Which ones would turn and which ones would move? The WASD would be the ones that move, right? So A would be moving to the left. Do here cam slide. How much in a second? Let's try 1 times delta time. That's another thing as well. That
you want that to be negative. Negative 1?
Yes, thank you. The point there was I'd like that to be a negative 1 because I'm going to left. That should be negative. And then D would probably be right. Let's just see what this does. Yeah, that's another thing with the separation of input and update, because I kind of like delta time to only be an update. So if I'm using input specifically, I'd actually use input just to set certain Boolean values, and those Boolean values will tell me what the update function should do. So are these buttons down? Should I be moving forward? Should I be, should my spaceship be thrusting? Should it be rotating? So I'd set these values in input and then use those values in update to actually change things. Right now, kind of checking this is like checking a Boolean value. It'd just be an extra step to do it inside both. Either way. So nothing is happening in all these. It's just A and D that should go to the left and right. So here's the camera going to the left. I'm pressing A. Here's the camera going to the right. I'm pressing D. But, still, I'm just strafing to the left and right. Let's add going up and down. That would be W. Should be what? Where should my value be now?
Y for the second one.
Yeah, so the second one, which is the delta V, or kind of the Y coordinates of the, which one should be positive and which one negative.
You should be positive, that should be negative.
All right. Now I can move to the sides like before. I can move up, W, down, S. Okay. So I can move around. It actually make more sense though that W and S would move closer and further away, right? If we're thinking about a first-person shooter. So let's change it to that. So where should this be then?
W and S, or
yeah, W and S, sorry.
That should be in.
So now it was going kind of up and down. It would make more sense to have this here. And then again, which one should be positive and which one negative? W should go into, that would be negative going forward, because we're working in the left-hand coordinate system and that has the z-axis pointing towards us. So going forward is going along the negative z-axis, going backward is going along the positive z-axis. if I've programmed everything correctly, that's the way it should work now. Going forward, going backwards, and going to the sides. But we kind of want
to get to a point where you can't see anymore. You go forward.
This will clip. Just go through it. And there's a specific distance that it clips at, so you can't actually go completely towards it. Again, this has to do with the projection. We'll learn it right next week. Just have to wait the weekend and we can talk all about clipping and projections and stuff. However, what we'd like to do is actually see the things from the side. Now we're just kind of moving forward and backwards and up. So then we need our rotation functions. So here, for instance, is yaw. I think that's the one we looked at on the whiteboard earlier this week.
Rotating y?
That's rotating around y, yes. Rotating around the u vector, no, the v vector. So basically that's looking to the sides. Like I have a stick through the top and bottom of my head and I'm rotating around that. Okay, so that's yaw. And yeah, not very human readable code, but the idea is just, we just take a cosine and a sine, and we're changing the u and n vectors, and we're just using the u and n vectors. The v vector, which is the one we're rotating around, both is not affected and has no effect, because that's the one we're rotating around. The other ones, and we take these cos and sine functions multiplied with those vectors into each other to rotate the right distance. Never mind, I have this all. So we have here roll, yaw, and pitch. So let's use yaw now. What buttons would we like to put yaw on?
Arrow keys left, right.
Arrow keys left, right. Okay. Let's try cam dot yaw. And now we need some angle. So the question is, this is only while I'm holding down the button. But while I'm holding down the button, how much do I want to turn? Like half a rotation per second? Does that sound too fast, too slow? So if I'd like to go 180 degrees per second, what number should I put in there? 180 times delta time. If it would be 180, if I only put 180, what would happen then?
Yeah, 180 per frame.
It would be 180 per frame. So if we try that one, it's, yeah, it's just, yeah, and it always goes exactly 180. So we never see anything in between. Either we're seeing directly away from it or directly towards it. Okay, so times delta time. It's pretty fast, but I like these things to happen fast, especially when you're grading. You just like things to happen fast. Okay, so that's us rotating 180 degrees per second.
I'm getting seasick.
So now I can move forward. Oh, okay, I'm actually rotating the wrong direction. So minus 180 here.
You lost your parentheses.
Yes, I have. So
now you have 120.
Oh. Thank you, Eclipse. All right. Now I can go both directions. Fine. Rotating, now I'm moving. So now I can actually move and rotate. So finally I can walk around this a little bit and see the actual 3 dimensions. Here you can see the clipping better. So just start clipping there in front of me as I'm kind of going into this wall. All right, so my scene is happening there. I can walk further away from it. I can walk closer towards it. I'm walking really slow. So what I'd like to do now is actually take this and speed it up a bit. So what do I want to do on the up and down keys? If we look at this here, I can go around. It's cool. Move around my scene and go a little bit away from it. Now we could actually start doing more rotations and stuff with that 3D model matrix we're going to make happen here. Yeah, on the up and down keys, we'd like to look up and down, or yeah. So yaw is looking to the sides. Roll is one option. We can try that one. That's actually around Z, roll. So what roll looks like, same values here. Change the ought to roll and put that on the up and down keys. The roll looks like is this. We're going at the same speed. It's pretty cool. So now the camera is rolling and the other stuff is going as well. So it looks like everything's just spinning in place. But actually, that box is doing that. Camera is just also doing that. And then we can go against it so we get extra speed. A bunch of fun stuff. Now we've actually offset ourselves a little bit. Using roll and kind of end up seeing everything from different angles. Pitch would have probably been a better thing to put. And then it just depends on if you're invert mouse or not, whether you want the negative value. So now we can actually go around here, look up and down, go under it, look back up, go all around it. Okay, to add something like up, down, just add R and F to the roll. No, Q and E, that's nice. Seems like going to the sides. We can do the roll there, so then we have everything. Let's see if it's the correct directions. I have errors. What did I do wrong?
Your roll takes an angle, not a series of points.
Oh yeah, okay. I copied the wrong thing. So this is the one I should have copied, like so and like so. Put the minus here on one spot. Roll. Okay, so I can roll as well, then I can go back, I can walk all around it, pitch, look at it from all sides. So the thing that's happening in the program now though, then I can roll, rolling the camera. Now I'm just changing the camera constantly. The camera is moving around. What's happening in the program is that every single frame, when I make a change to the camera, I'm just calling these functions that make a change to the camera's coordinate frame, to U, V, and N, and to I. So these values here are just changing. I'm not sending anything into OpenGL when I call these. I'm just making incremental changes to my own data structure, which is the data structure camera, and it has 3 vectors and a point.
And then in draw, when you do get matrix.
Yeah. Then when I draw,
get view matrix, it sends it all out.
And it kind of fits with this idea of doing all these changes in update, but when you display, you just take what you have and you draw that. You're not changing anything, you're not moving anything with OpenGL. You just take what you have and you draw it. So we make all these changes during update, all these different changes with all these different buttons. Then finally, we just call view matrix and it just takes these the way they are, makes a matrix, sends it out. What we have, just make a matrix, send it into OpenGL. Okay, so now we have a way of moving around. Now we might be able to play a little bit around with our scene. Let's go into model matrix because there we only have add rotation to Z here. If we take this function, we're going to do an add rotation X, rotating around the X axis. What do I change here in this code? Raise your hand if you understand this code and can make correct changes to it. Half a hand there, that's more or less a whole hand.
I understand the code, but it takes me a minute to understand the change.
Okay. So this is rotating around Z, seeing that this here third column and this here third line, they have to do with Z, and they're just identity.
So shift over and down.
Yeah, so shift 1 to the right and down. So minus sign goes from there to here.
No, it doesn't go 9.
Oh, no, and down, sorry. To here. All right.
And then
Cosine goes from there to here. Sine goes from here to here.
cosine stays.
And cosine really goes from here to here, but it's also cosine there.
0.
So this one 0, this one 0.
Shouldn't 0 be 1?
Yes, yes. This 0 should be 1. It should be identity matrix. Thank you. I have a good audience that actually helped me get this right. Since most of the students will be watching this on the video, it's better to have it correct on the video. All right. So yeah, this should more or less do what we want it to do. Then we can go in here and see how that works. First, we can simply look at what the scene looks like exactly now. Back a little bit away from it and it looks like that. If we simply go in now and change our rotation z's to rotation x's instead. A lot of nothing happened. Add rotation x, model matrix, add rotation x. Is there anything in particular that I did wrong here? Right, let's try to skip one of them and just do one. Okay. Who can tell me why this happened? I'll even go so far as to do a one note here. Again, data structures. All right. How you guys think? What exactly happened? Why didn't at least something happen?
You negated the rotation back.
Yeah, I'm always negating the rotation, but that was okay. That was okay when it was z. Why wasn't it in x? Yeah, the translation was along x. That was kind of the key. Earlier, we'd have this coordinate frame here, and then we'd rotate it in this dimension. Then we'd move it along this axis, which then, you know, after the change would be this axis. And then we'd rotate it back, so it looks nice again. In the other case, we were rotating around x, then translating along x, and then rotating back. So if we imagine that being y rather than x, we say, or z, we can say we're rotating around z, like this. Then we're really moving just forward into the frame or backward. And then we're rotating back. And so the dimension that we're rotating around didn't change.
So if you wanted to change that, you would change your translation to be translating on a different
axis, yeah. If we rotate around x and want that to have an effect, we have to translate either along y or along z. So let's just try that by doing the same, except have the translation be up to begin with. So if we skip these here, then we're just translating by y, which means it goes directly up. So it's there. Then we start rotating the coordinate system. Then we're going to get this rotation here. And then we can do something like adding another box and saying, all right, we can imagine that that's kind of some kind of moon, and then we can put a satellite around that moon. And now we can actually make things translate a little bit further. And let's say, okay, I've gone from here to here. I can draw this, but I want to do more. I want to kind of do the whole thing again, except I don't want to pop just yet. Draw the cube there. However, I kind of want to push here. I still want the push here, I just want an extra pop because I don't want that scale. That scale is just to make that particular satellite a little bit smaller. So let's make that one a little bit bigger. All the wrong buttons here. Make this one a little bit smaller. And let's take the first one and rotate it in Z and translate in X like we did before.
Rotation
Z here. Then we draw this one and pop it, but we're still there. We're still out there in the correct position. So now we're going to rotate around X. We're going to translate a little bit shorter though, say 1.2 along Y, and then going to rotate back around X. And we can actually, we don't really need more rotation angles that go faster or slower. We can make this one slower. So we can just say, I'm going to make this rotation a little bit slower. Now I can see what happens. It would be cooler to make the other one slower and this one faster. Or the same. Rotation angle here times 0.5. Sorry, it's getting pretty cold in here and my fingers are freezing up. It's all right though, we're almost done. Okay. This is going in that direction, the other one in the other direction. That looks pretty cool. However, I might say, well, I also want some kind of internal rotation on that last one. Maybe we can go ahead and do a, after we scale, or before we scale, doesn't matter. Rotate a little bit around the y-axis. But we don't have that function, so let's go ahead and make that one. How would that one look then?
You move over and down again, but wrapping.
Yeah, I kind of wrap it. So this one goes, minus S goes up to here.
Wait,
this one becomes 1. Cosine sticks to 1. S kind of goes down to here, which wraps it up to here. No, yes, that's true. The S, the cosine would have gone here. This one minus goes, yeah, minus goes to here, wraps over to here. Whereas the sine goes down and up and wraps over to here. Should make it as here. This one becomes 0, this one is 1, this one is 0. Is it correct now? Cos 0 sine, 0 1 0, minus sine 0 cos. This one is supposed to be named y. It's hard to see there. Go to somewhere where we can see it at least when it comes in closer. Wait a minute, is it changing its rotation around as well?
No, it's still rotating around like it was.
We're supposed to be rotating only. It's rotating around the way it was, isn't it? Ugh. Messes with your head. Play around with these things. Anyway, then if we want a satellite around that one, we'd simply take this code here, you know, stick it in after you draw the first one, somewhere to here, and you know, see what happens from there on. It gets tiny because it didn't kind of undo the scale as well. So yeah, need to pop the scale and pop that, then we need to push after, so on and so forth. Maybe I'm doing too many pops and pushes. All right. Anyway, is that time up or is it 5 minutes still? Any questions? Anything you want to see happen here? It's always fun if we can just kind of look at things happen. Other things that are here are something like sphere graphic. They're not as interesting when we're rotating, since can't really see them much. Draw a solid sphere. At least make the first one that way. Is it? It's a sphere as well. It's a very, very tiny one. So, a bunch of cool stuff. How can I make this? What am I doing wrong with the scale? The scale here is popped off. Scale here is popped. And we need, isn't it? No, there's another push here that just pops the scale. Yeah, that's what we need to do again. Another push before the scale.
And then
another pop after the draw. Actually get it in a inside. Yeah. Rotating all over the place, but it's rotating around the small box. So the small sphere is rotating around the small box, and the small box is rotating, you know.
It actually looks
so
like
everything's rotating around each other.
right.
Yeah, it ends up being rotating just all over the place. But all the rotations affect it, so that's why it kind of doesn't seem like it's rotating around one angle. It's just, or one ellipse. It's going all over the place. So more or less, this is what you need to do, kind of the next programming assignment, which is kind of setting up a maze. You just need to be able to take these boxes and scale them so they're walls instead of boxes. Then just set up some data structure that kind of takes those walls or those boxes and puts them in the correct places. And from then on, just collision detection again and stuff. But yeah, the only thing, well, we can go into later into more complex ways of doing things more optimized, but more or less you could set up a nice environment with walls and stuff just doing this and use that to get a feel for traveling around with your camera. Just getting a feel for kind of what effect does the camera location have, what effect does all the model matrix changing have. So if I let go of the keys, all the motion that's happening now is happening through changes of the model matrix. As soon as I start pressing the keys, I'm actually affecting this by changing the view matrix. So both of them end up being geometrical transformations, but you know, one is affecting the point of view, the other is affecting the position and orientation of what we draw. Yes.
How would you collision detect that you're gonna go into the square or into something? So like if you walk directly at the square and it directly at the square and it clips, if that was a wall, you shouldn't be able to walk through it.
I wouldn't be able to walk through it. So if it's an arbitrary wall, what we're going to be doing in our assignment is most of you will just have walls that are parallel and perpendicular to the axes of the coordinate system. So you can actually think of it as a grid and just say, where am I in my cell? And if I'm too far to the outside of the cell and there's a wall there, no, I'm going to stop my Y direction. No, sorry, my X direction or my Z direction. So it can be done simpler. But if it's an arbitrary square, then what you can do is you have the camera class. So if I'm walking forward like this, so if I simply detect the button for walking forward is down, that means I'm walking along my negative n vector. So there I have a vector C for collision detecting. I can take my camera's position in get origin. I can get the C vector into the collision detection by saying I'm going to take the negative n from my camera. So I get the n, I negate that. That means I have a vector that points in the direction I'm going. If I hold both forward and to the side, I simply have to add those vectors up. I take the u vector, I add it to the n vector. One or both may be negative, depending on if I'm going left or right or backwards or forwards. There I have my vector. The camera's position is the point A. So there I have that. Then here I simply have a position of one of these points. I have the plane that this side lies in, and then I simply set up my t-hit calculations. But in 3D, then it's array to a plane rather than array to a line because 3 dimensions.
Yes.
But yeah, that's what you do. You just take the information you already have in the camera, set up your calculations, and get to hit. Cool. So now time's up. Have a nice weekend. See you all next week.